let's going to start to be on time. So,
Okay.
Good afternoon, good morning, everyone. We are going to start the session, which is going to discuss about the data science in astrophysics. Our first speaker is Mohammad Hossein Zhollideh from IPM and KNTU. And he's going to talk about classification the stars using photometric optical data of SDSS. Mohammad Hossein, the stage is yours. Please go ahead.
Thank you, Soroush. Thank you. Hello, everybody. Before I start my presentation, I would like to thank local and scientific committee of this great event, and especially thanks Soroush for his efforts and time. And I have seen how much effort he has made to run this conference smoothly and professionally. Anyway, today I'm gonna talk about machine learning and its application on astronomical data. My presentation will have two parts. In the first part, I'm gonna talk about general concepts of machine learning and some popular algorithms, just in order to, as an introductory part, to let you know what is machine learning. And in the second part, which is a hands-on practice, I'm gonna solve and show you an actual problem, astronomical problem, and classify variable stars and from main sequence stars. I will go in more details in the following slides. By the way, I have copied and pasted the link, which is a Google Drive link. You can click on it in the second part and have access to the Google Colab that I'm gonna talk about and solve the problem. Anyway, okay. We are actually, to begin with, we are actually in the big data era. And, ground-based and space and sky surveys and telescopes are gathering a tremendous amount of data for us every day, continuously. And as an example, you can see here, for example, ground-based radio telescopes and optical telescopes and other telescopes, and also sky telescopes are collecting data in different bandwidths. And nowadays, we are observing electromagnetism, frequencies and electromagnetism waves in different bands, from radio frequencies to gamma rays. And as you can see here, there are some selected sky telescopes. For example, you can see Planck here, Euclid, XMM Newton, and different types of sky telescopes which are gathering data every day. And to add to these observations and surveys, we are collecting data of gravitational waves and neutrinos, and you can imagine how much data we are encircled with and we are gathering. So when we talk about big data, it has some characteristics and features. Big data is big in terms of volume, variety, and velocity. And volume, as you can guess, is the amount of data that we are working with. Big data propose some challenges. It's hard to capture, to clean, to store. It's super difficult to process big data and analyze, visualize, and everything could be super complicated when it comes to big data. And to have a sense about big data and what we mean when we say that we are just entered or facing big data era, I have brought for you this plot in which you can compare different surveys. For example, VLT. You can let me.
Mohammed Hussein, can you hear me?
Yeah.
Could you please make it full screen to maybe that would be.
It is quite, because I want to write something, I couldn't full screen this. It's a PDF.
Okay, no problem.
Okay, so you can see that, for example, VLT every night on the vertical axis, you can see the data gathered by different surveys and telescopes overnight. And VLT collected 10 gigabytes, for example, which is almost the size of USB that many of us have in our backpack or in our pocket. Then SDSS gathered around 200 gigabytes, which is almost the 20 times the VLT. And then we have Vista, LSST, and when you look at LSST, you can see that it's 30 terabytes and TMT 90 terabytes, and it's almost 90 times 1 tera hard drives, external hard drives that most of you have. And you can imagine how big this amount of data is, and these are just observation overnight. Variety. We are facing a wide variety of data type in astronomy. We have, for example, we can work with images, we can work with fluxes and spectra. We have time series and light curves and temperature fluctuations, and also we have data of simulations. And you can see we have a wide variety of data types in astronomy. Velocity. Velocity means a speed of producing, transmitting, and analyzing. And to have a sense about velocity, for example, LSST will generate 1 SDSS each night, and it will continue for 10 years. Every night, each observation of LSST is equal to SDSS. And here you can see LSST and SDSS, for example, and LSST expects to find around 1,000 new supernova each night. And as I said, it will continue for 10 years. This velocity of data production is unbelievably high. And how can you, for example, classify? How can you, for example, analyze, clean, and do data analysis and follow-up observation on this tremendous amount of data? Okay. So to put it simply, it is a golden era for astrophysics to deal with challenges and opportunities that are caused by massive data volume, rates, complexity by the next telescope. And data mining will be super important. Let me put it somewhere else. My Soroush, this camera, some windows are preventing me to see some part of my slides. Do you have any solution for this?
But we can, it's better to put it away or somewhere else, because you don't need that actually.
Can it be done?
Yes,
I cannot
yes.
close it.
Yes, but put
How
it
can
somewhere.
I close it? I should, for example, drag it.
Yes, to drag it or use some option to minimize or collapse it.
Okay, let me make presenter. I don't know.
Otherwise, you can use this full screen.
Oh, I found it. I found it.
Okay,
I found the solution. Thank you.
Great.
Yeah. And as I was talking, data mining is of great importance in the big data era. And it will help physicists and astronomers to, for example, discover new things, and maybe some scientific breakthroughs happened when we analyze so much data. And the data mining tasks includes mainly summarization, classification, and regression. It also includes clustering and anomaly detections and outlier detections. So in order to tackle with so much data, we cannot use conventional methods, and we have to use some state-of-the-art method and techniques. Machine learning is one of them, and it has shown to be a promising approach to tackle some challenges that we are facing and we are gonna face in big data era. But what is machine learning? There are different explanations and definitions for machine learning, but one of the best that I really like it is given for you here. Machine learning is the science of getting computers to realize a task without being explicitly programmed. And those who are familiar with programming know that to do a task from scratch and without using machine learning method, you have to write hundreds of lines of codes. And on the other hand, if you use machine learning methods and algorithms, you can solve problems in a few number of codes, which you will see in the hands-on parts. And where can machine learning be used? To answer this question, I should say that where machine learning cannot be used, and it's used every day in different parts. And you can see that in your Google searches, in, for example, phone reply systems, and even COVID-19 and determination of whether, COVID-19's diagnostic and speak recognition and self-driving cars. Every aspect of our life nowadays is affected by machine learning. And I really like these slides because in a single slide, you can have a view about machine learning. And if you consider machine learning as the central concept of this slide, it's mainly divided into two branches: supervised learning and unsupervised learning. And supervised learning is can be divided into two main parts, regression and classifications. And you can see here different algorithms. For example, support vector machine, k nearest neighbors, decision tree, and here for regression, you can see regression analysis, regression tree, and other algorithms. On the left branch, you can see unsupervised learning, which I will explain in more detail. And here we have usually dimension reduction. You can see here with different method like PCA, principal component analysis, and factor analysis, and other methods. And we have clustering. And in clustering, for example, we can use k-means and Gaussian mixture model and other models. And one state-of-the-art branch of machine learning that Wang and Rahim are gonna talk about is deep learning and neural networks. I don't go in details about this, and you can hear about this section from other speakers after, after me. So I told you machine learning has two branches, unsupervised and supervised. And I talked about this slide previously. So supervised learning, what does supervised learning mean? In supervised learning, we define a cost function, which is something like this. You can see it here. And our goal is minimizing this cost function. And in this cost function, you can see we are subtracting a function which we call it hypothesis. Hypothesis can be as simple as a linear function to a more complicated function. And by minimizing this cost function by using hypothesis, we actually find these parameters. And when we find theta 0 and theta 1, our task is done. And when we have H, we have a boundary, decision boundary, by which we can classify new and unseen data points. What's happening here is like, for example, suppose we have a data set, blue and red, or 0 and 1. You can consider colors as label, or these you can consider these as 0 labels and those red one as 1 label. And the task of machine learning is finding this boundary. You can see this green boundary, and this is called the decision boundary. And by minimizing cost function, we find this boundary. And then after finding this boundary, if I give you, for example, a new data point, suppose I give you a data point here and ask you whether it belongs to the red part or blue part, because it's on the right-hand side of our decision boundary, you would say it belongs with a specific probability to the right-hand side and to the red points. And this decision boundary can be very super simple, just right, or super complicated. And surprisingly, this boundary is not very well, although it works very well for this data set. It separates all circles from crosses perfectly, but on a new data set, it won't work, and it is called overfitting, and the left-hand side is called underfitted data. So let me talk a little bit more about supervised learning. I told you supervised learning is gonna be finding a decision boundary, something like this. And after finding this decision boundary, we can, if we are given a new data point, for example, this one, we can determine its label. And in supervised learning, we have both features, x1 and x2 are features, and we have labels. Here, labels are, for example, these stars and these circles. These data points are all belong to a star category, and these circles belong to circle category. And we can compare it with unsupervised learning. Unsupervised learning, we are not given labels, and it's just machine should distinguish labels. And compare unsupervised learning here with those that I showed you in the previous slides. Here we have features which is x1 and x2, but we don't have labels. Every point is look like similar. Compare it with these data sets which we have. For example, we have stars and circuits, but here in unsupervised we have just features, not labels. Now it's time to talk about ML in astrophysics, and there are different tasks that can be done and by machine learning: spatial clustering, source classification with images, object detection, data cleaning, inferring stellar parameters from spectra, and signal detections are some of the domains that machine learning has been used in astrophysics. I'm gonna talk about a few number of them. For example, here we have K-means clustering. I don't go to details of the algorithm, but this algorithm can distinguish there are some clusters. It can, in the feature space, it is the feature space. And in the feature space, machine can distinguish these data points belong to the same category, these to the same, these to the same, and so on and so forth. And this can be done by an algorithm, machine learning algorithm called K-means clustering. And in order to, just a minute, let me, okay. And the phone was ringing. I'm sorry for that. And yes, this is an algorithm called K-means clustering. And by this algorithm, people have shown that have found a cluster and groups of galaxies in SDSS survey. And you can look at this paper and find more details about this. Source classification with images is another application of machine learning. You all are almost familiar with Hubble tuning fork classification. In this classification, by looking at different types of galaxies, you can classify them to elliptical, spiral, bar, and different types of galaxies. And previously, it was done by human forces and by scientists. But nowadays, thanks to machine learning, this task can be done by machine learning methods. And Galaxy Zoo project is one of the most popular approaches to classify galaxies. And neural network is another algorithm for machine learning. As I told, Rahim and Wu will talk about neural networks more, so let me skip this slide. By using neural networks, we can find objects in images. And people have in computer vision and in artificial intelligence has developed some approaches and algorithms to find objects in an image automatically with high accuracy. You can see accuracies here. 99, 97, and close to human accuracy. And these images were not seen before by machine. This is the magic. And similar phenomena can be, similar approach can be done and applied on, astronomical observation, which we have done a similar method, some CNN based, convolutional neural network methods on SKA radio images. We have done it in SKA Data Challenge 1, and we could find, you can see, radio sources are found in these images, and very nice. And morphological classification is another, task that can be done by machine learning. In this paper, you can see how radio sources can be classified into different classes. And because I am running out of time, I would skip this slide too. And this is the architecture that is used in that paper. I wanted to talk about it, but let's escape and go through GAN, generative adversarial networks. This is a popular and a state-of-the-art network which has two main parts. It has a discriminator and it has a generator. And from random noises, the input of network is non-random noises and some images. This part tries to generate some images from random noises, and this part tries to distinguish whether the input image in this part is fake or authentic or real. And after training these networks, you can generate, as you can see here, some images that these people don't exist in real world. These are real world human beings. They are all generated by this approach. And similar approach can be applied for galaxies. And here you can see that in this paper, Siamak and his collaborators has generated galaxies because they needed high resolution images of galaxies, and this is super expensive to collect these data, and they generated their necessary data via GAN. And you can see here in the second row that these galaxies are generated. So it's time to go to the hands-on problem. And in the hands-on problem, I'm gonna show you how to classify RR-Lyra variable and main sequence stars. And before RR-Lyra variables are some variable stars, pulsating horizontal branch-out stars of spectral class A or F, and their mass is around half the mass of a sun. And there are some green points here. I don't know whether you can distinguish them or not in this part. This is color magnitude diagram. These parts that I'm showing you belongs to RR-Lyra variable stars. And we are gonna, the behavior, these are variable stars. By time, their magnitude changes, and we are gonna separate them from main sequence stars, and by using color magnitude data. Soroush, would you please let me know how much time I have? I wanna manage my data, my time.
Let me check. Yes, actually, I think you have 15 minutes.
Oh, great. Thank you very much. So okay. It's time. I wanted to talk about precision and recall, but I escape it and I go directly to the ICRANet notebook that I have prepared for you. You can click on the link that I have pasted in the chat box. You can have access such a notebook. First we launch Google Colab. But in order to run this, you should shift enter. And after you shift enter, you can see that something happens here, and it run. And I'm gonna use some, while it's running, I wanna say that I'm gonna use some, yes, and such a link will appear. You click on it, you will come here, you click on your account, and yes, you sign in, and then you can copy this link here, come back here, paste it, run it, and there you go. You will be well prepared to use Google Colab and the free GPU, RAM, and disk available for you by Google. I have brought for you some explanation about RR Lyra. You can see that running has finished. You can see a green tick here, so you can go ahead. Let me go ahead. And yes, before doing anything, you need to install AstroML, because AstroML is a package that I'm gonna show you here. You can pip install AstroPL, and it will start installing it. And AstroML is a package. If you Google AstroML in your search, the first link that pop-ups will be AstroML. You click on it, you can go to AstroML, and here you can have access to astronomical data, some pipelines for astronomical data cleaning and machine learning with astronomy. I have brought for you an example from AstroML, and there are different examples. Here you can find a good book and download it and take a look at it. And here you can find some example. For example, dataset examples. You can access SDSS spectrum. For example, you can have access to WMAP plotting. You have access to WMAP power spectrum, and SDSS galaxy colors, SDSS images, a wide variety of astronomical data will be available for you. So after installing AstroML, it's time to import some packages such as NumPy, Pandas, Matplotlib. Those who are familiar with Python, let me zoom in to show you better. Those who are familiar with Python know how to import, and we are gonna import some packages. For example, from AstroML datasets, AstroML utils, and we are gonna use scikit-learn. So let me show you something about scikit-learn here. So if you Google scikit-learn, again, the first link that pop up will be here in scikit-learn. It has a great documentation. We are not gonna write codes, machine learning codes from scratch. Although we should have deep insight about algorithms, we can take advantage of packages available here. For example, linear models, for example, support vector machine. These are different algorithms available in scikit-learn. And for example, for classification, and click on it, you can, it has a great documentation. It explains about you in detail, and you can do some, hands-on problems and figure out about details. And it's a great resource for learning, machine learning, and applying machine learning algorithms for your projects. So here let me show you this plot. In the first part of hands-on problem, I'm gonna generate some data. These data points are simulated. They are randomly produced by me, but they have some features. You know, there are two labels, class 0, class 1, blue and red, and there are two features, x1 and x2. And in this feature space, our goal is finding this boundary decision. But you know, our machine learning task will reduce to finding this boundary. And look at this, the mean of feature x1 and x2 both are 1 for these sets of data, but for these sets, the mean of x1 is 5, the mean of x2 is 3. Let's go back, and here I simulate some data. You have access to this data, so I don't explain more about it, and you can easily generate them. And after generating those data, it's time to define our classifier, our machine learning, algorithm. I choose logistic regression, and I name it, my classifiers will be logistic regression. So simply, it is 2 lines of codes. It is magic. You know, it's the beauty of scikit-learn, because you can, by 2 lines of code, that's it. You fit when you type and write clf.fit x and y. X and y are defined in the previous section. I told you how to produce them. Take a look at it. You can generate x and y, and that's it. By writing this code, you fit your model, and then you can predict. clf.predict can give you z, and in the following, here I have provided you some lines of code by which you can plot both your generated data points and the decision boundaries. So in 2 lines of code, you could define your model, logistic regression. I didn't have time to talk about logistic regression for you, but it's a machine learning based model, and then fit it. And after that, that's it. You are done. You have finished your task. So it's time to go and analyze real data. So here, once again, I redefine my data. I use real observations in main sequence, colors, and RR Lyra colors. And by this line of code, you can load all data you need from AstroML. And when you print the shape of your data, you can find it here. It has 93,141 rows and 4 columns, and labels are as well here. And you can make it, data frame, and look at your data in your data frame. So you can, if you are familiar with astronomy, these are colors, and these are first rows of our data. So as I mentioned, so there is a routine and function in AstroML which separate, you need to separate your data into training set and test set. And this can be done by this function from AstroML. You define some numbers, number of your training, number of your tests. And here is again the part that I'm interested to focus on and explain for you more. You define your classifier, logistic regression. Again, you type clf.fit X train and Y train. I use just 2 columns here, and you can have your data predicted here. So after that, you can, for example, let me run it. These things. Let me run these boxes for you to see how it happens. It takes a while, but I want to show you how it happens, and all things can be done smoothly and easily. Okay, and here, for example, you can find your, for example, and here again, I don't wanna spend our time for running these cells, but you can do it easily. And here you can look at these things and ask me your questions later on. Everything is available for you. But here you can fit your model as I explained for you. Here you can fit it. And you can have predictions on your test sets, and then plot results. I just want to show you results. So this is a real world data. And you can see that in GRUG, these are, as I told you, colors of our data, our observation. And these purple points are for these purple points. Pink points are, showing RR Leroy stars, and those blue points are showing main sequence stars. And this is a decision boundary produced by logistic regression. Let's analyze our final. Let's use, there are some, for example, metrics to measure the accuracy and the validity of our model. For example, accuracy, you can use accuracy score. You can see it's around 97% accurate. But there is another important metric, which is F1 score, which is not quite large. And you can see here there are some blue data points that are in the lower panel, and it's a feature of real world data. I change my classifier. Previously, I was using logistic regression, but now I use Gaussian bias. It is another algorithm. If I fit my model with this method and plot my data, you can see the decision boundary is not a linear line. It is a curve. It's a higher dimensional. It's not linear. It's a polynomial function. And you can calculate accuracy and F1 score. And there are recall, for example, precision. There are different metrics that you can use and check which algorithm is working better and more accurately. I think I'm running out of my time, and I asked Soroush whether I have more time or not. I'm almost finished, but if any individuals has any questions, I'm available, and I hope I have finished my presentation on time.
Yes, actually you are pretty on time. And I think we can have some question or comment from audience. So is there any comment? Is there any comment, question? Let's ask the participant if they follow your coding. I see in the chat some of our friends tried that Colab
Okay.
code.
They want access to the notebook, so I paste it once again. Let me.
Yes, actually, just I want to mention that all of this information also indicated in our Indico webpage. We have one session to have all of this information there. So you can simply go there and check the website. So
yeah.
So is there any question? If there is no, let's thank you again, and let's move on to our next presentation, which will be given by Rahim Moradi.
Okay.
Yes. Thank you so much, Mohammed Hussein.
Thank you.
For the very interesting talk. And actually, I was following your steps, and I produced some of these beautiful plots.
Good to hear that. Thank you. Thank you.
Thank you so much. And we share all of this content to our audience in this Indico web. Rahim, can you hear me now?
Yes.
So great.
Okay.
So our next speaker is Professor Rahim Moradi, who is from ICRANet, and he's going to talk about some topics on the data staff in GRBs, and also he will talk about this classification of astronomical object and determination, the redshift using a spectroscopic optical data of SDSS. So, Rahim, can you please share your screen?
Let me see. It's inactivated. Sharing my screen. Can you?
Yes, let me. Okay, now you have to. So, can you share now?
Let me. Can you hear my screen?
Yes, great.
Okay. In spite of what we. Okay. Hello, everyone. Thank you, Soroush, for organizing such a informative and advanced meeting in collaborating with ICRANet of Italy. I was supposed to talk only about, let me see if I can. Okay, I was supposed to only talk about a spectroscopic determination of redshift and classification of astronomical objects using deep learning and convolutional neural network. But after a bit discussion with other organizers, we decided to talk first around 15-20 minutes about our recent understanding of GRBs, and then going through this equally important deep learning era. So first I will be talking about the nature of ultra-relativistic prompt emission phase of GRB 190114C and GRB 180720B. These two GRBs, I will explain why we call them like this and why they are very important in our GRB analysis. This work has been done under the supervision and is a group of Professor Ruffini, with collaboration with Zhollideh, Liang Li, Bianco, Campion, Cherubini, Filippi, Wang, Shue, and Rastegani. Okay, two short review about GRBs, and as you may know already, the GRBs are divided into two groups based on their observation. If the explosion is shorter than 2 seconds, we call them long, short GRB. If it is more than 2 seconds, we call them long GRBs. And the main interest for this burst is that in less than 100 seconds, they release energy around 10 to 54 Earth, which is equivalent to mc square of mass, totally mass of sun goes to energy in like 1 second to 100 seconds. So this has become very interesting for astrophysics community to know what is exactly behind these sources and what is producing this energy. How we number the GRBs, for instance, this GRB is 180720b. 18 means year 2018, 7 is month of July, 20 is day 20 of that month, and B, when there is more than 1 GRB a day, we call them A, B, C, D, and whatever. Usually around 3 or 4 GRBs in a day are observed by different telescopes. One of the most interesting GRBs, 19114C, around 2 years ago, was GRB 19114C, which in our classification is a binary-driven hypernova, which I explain a bit what it is. Here it shows the total light curve. First, like 100 seconds, the energy is around 10 to 53 Earth. We have different episodes in this GRB, but what makes it, we call it binary-driven hypernova, is that we did with help of Liang Li, the analysis of the time result analysis and time integrated analysis of the GRB. In general, it has around 10 to 53 Earth energy. It has observed JEV emission. It has the thermal component observed in the prompt emission, which we call it ultra-relativistic prompt emission phase. And the luminosity in that phase follows this behavior. All this, and together with the X-ray afterglow of this GRB, we noticed that it should be in our classification a binary-driven hypernova type 1. So at this time, Fermi GBM observed. How to put this down? Okay. The Fermi GBM observed and got triggered by this GRB, and after some seconds, other satellites were triggered by this GRB. As soon as it was triggered by Fermi GBM, Fermi LAT, another detector on Fermi satellite, started to look at it and observed high energy JEV emission from the 100 MeV to 100 GeV. It was observed by this detector. And after the redshift determination, which without redshift, study astrophysical object is almost impossible, and that's why the redshift estimation, either by human or by deep learning, is very important. After knowing the redshift, we calculate the energy. We noticed that it's a binary-driven hypernova, and in our model, it was associated with the supernova explosion. So we predicted that supernova explosion that has made this GRB must be appeared in optical band around 18 days, which indeed was confirmed by Melandri et al. And the peak of supernova, optical supernova, was also observed by this group. So this successful prediction, which is not only for this GRB, but since this GRB has a set of very complete data, made us to analysis at the BDHN. So what is BDHN? In short, if I want to explain the BDHN theory, we have a carbon-oxygen core which undergoes a supernova explosion. Then as a remnant, the new neutron star will remain, and the supernova explosion will go to the binary companion neutron star. If they are close or some other conditions, neutron star will undergo a black hole. And what happens in the black hole activity? We will see this GRB. and we call it the BDH, binary driven hypernova of type 1. And if instead of black hole, we have more massive neutron star, we'll go to the binary driven hypernova of type 2, which here we are encountered by a type 1 binary driven. And this model also has been incorporated by well-known director Tornatore in one of his movies, 2016, which part of the movie is about this model. So we say that in the BDHN model, the BDHN type 1 model, black hole plays an important role. How? When we have a neutron star, we have accretion on it, and we have black hole formation. These are two simulations, one by Wilson, another by Redsoll et al. It shows that since the neutron star itself has magnetic field, after the accretion, this magnetic field will be amplified, and we will be left by a rotating black hole, which can be a Kerr black hole in presence of the magnetic field. So we know that we have a rotating black hole, and this is the Professor Kerr, Professor Lofini, Wang, you, and me, which first proposed this rotating black hole, and which later Professor Lofini proposed with Christodoulou, and later by Hawking, the mass energy formula of Kerr-Newman black hole, which when we have charge Kerr black hole. So it was a very pleasure discussion with these people who are owning this formula, which we could use with them to establish our theory of the black hole inner engine. So what's the idea? We have a black hole, Kerr black hole, we have a magnetic field, and there is a Papa-Petrov theorem which tells that if we have a vacuum space-time, axisymmetric vacuum space-time, the Killing vector in that space-time can be written as the Maxwell field. After some assumption, Wald finally solved this problem when we have asymptotically uniform magnetic field aligned with the rotation axis. These are the formula that first were represented by Wald, known as the Wald solution. So this electromagnetic field are for the black hole in presence of a test magnetic field. So first, in one of our papers, if I want to briefly talk about this paper, one of our paper when we incorporated this model to explain the jet emission coming out from the black hole, near the black hole. We explained the jet emission, which its behavior in the luminosity follows the power law, which I noticed one of the audiences asked this question. This power law shows that we have the near the black hole in this jet emission, we have synchrotron radiation of the electrons or the proton, which we here consider electron, when they are in the external electromagnetic field. So under three conditions, we calculated mass and spin of black hole. First, that extractable energy is, which is rotational energy of the black hole, is paying the energy of observed jet emission. Then the second one was this synchrotron J photon must not be in presence of the magnetic pair production. And the third one, that observed time radiation must be equivalent to the time of the synchrotron. And after solving these three equations together, we will have the mass and spin and the magnetic field around the black hole. As you can see for GRB 9114C, mass is around 4.4 solar mass, magnetic field around 10 to 10 Gauss, and spin parameter A over M 0.14. So what happens in the ultra-relativistic prompt emission phase when we observe the thermal component, and we observe in the case of GRB 9114C only 2 seconds of observation, we observe this thing. What's happening here is that first this idea was proposed by Damour and Ruffini in 1975, then was developed in a series of work by Ruffini, Salmonson, Wilson, and Schue, starting from 1991, as an explanation of the inner engine of the central engine of the GRBs. And what's the story there at that time, at that year? They considered the Kerr-Newman black hole or Rising-Rosen black hole, which is highly charged, which we solve this problem here, which we represent that black hole cannot be highly charged. But the first idea was very important, that when we have this charged black hole, around the black hole we have the electric field more than the critical value of vacuum polarization, then there would be E plus E minus plasma. When E plus E minus plasma is created due to its high internal energy, internal pressure, it starts to expand, and after around when it flies over like 10 to 11 centimeters away from black hole, it starts to radiation, which we see as this thermal component plus other component in this area, only 2 seconds of the prompt emission phase. Which we have published recently in Physical Review D, this work, Nature of 1901, Nature of UP phase of GRB 9114C. So what is story? Again, we have the same inner engine, magnetic field, the black hole, rotating black hole inside the external magnetic field. And what we have, that in analogy with Kerr-Newman black hole, we will have that this the place that we have over critical field we call diode region, and this diode region, which I said it's place that we have over critical field. The formula of the energy of diode region has been calculated by Cherubini et al. If I'm not mistaken, 2009. Which if we do the analogy with the Kerr-Newman black hole, instead of Q, we work with 2B0J. And I will explain more what is the 2B0J in terms of the charge of the black hole. As you can see, this is the lambda, this charge to mass ratio of black hole, 2B0J. So here it says that in the first principle, there is no charged black hole, and whatever it is, there is an the gravito-magnetodynamic interaction of the black hole with the surrounding magnetic field. B0 is the magnetic field, J is the angular moment of black hole, which finally this interaction will give us the effective charge of the black hole. And when we solve this equation based on, which I will explain later, first we have this E plus E minus in the presence of black hole. It expands, and then at around 10 to 11 centimeters, we have this radiation. What we need to calculate the characteristic of this expanding shell, if the first one is its isotropic energy, the second one is the ratio of black body to the black body energy to the total isotropic energy, then the value of the observed black body, and at the end, the width of this flying shell. And if we set in a way that at the end of UP phase with only 2 seconds, 2 to 4 seconds. At 4 seconds, we have E equal to E critical, and after that it drops the electric field. We'll obtain that energy of the other region is around 10 to 45. Time scale of each impulsive process is around 10 to minus 9. Radius of transparency is around 10 to 10, and the gamma factor of each exponential is around 100. So what we have, instead of one exponential, a continuous observation, as many people consider, we have in 2 seconds many discrete exponential, which time scale of the observation is around 10 to minus 9. But unfortunately, due to the low resolution of our observation, we can only go to the resolution of around 0.1 second, not less than that. So this will give us the real understanding the UP phase, which tell us finally the Q over M of the black hole, which is not because of black hole is charged, because it has electromagnetic interaction with magnetic field. It is around 10 to minus 5. So in principle, there is no charged black hole at all in the universe. And if in this small step there are some effective charge, this will produce the ultra-relativistic prompt emission phase of GRB. Another GRB that we have recently studied with our PhD student here at Stekarnia is that the GRB 180720b. This GRB also has a complete set of observation from the moment of supernova rise in the MEV radiation from the to UPE phase, hard X-ray flare, soft X-ray flare, and finally the late time X-ray afterglow and the associated optical and radio observation related to this late afterglow. One thing that I should mention, the black hole physics explain the UP phase and the JEV radiation. And since in the BDHN model, we have neutron star companion of the black hole, that part, accretion of the supernova onto the new neutron star will explain this last part, which is not the subject of this talk, but I wanted to just mention. And as you can see the preliminary result that we have found, thanks to Liang Li, the thermal component with high resolution in this area, which in turn can help us to find the characteristic of the UP phase. Again, this one gamma is around 30 less than other bursts, but time scale is around 10 to minus 9. And as you can see at the end of UP phase, which is again 2 seconds, 1.5 seconds, E is not E critical, and the radius of transparency is 10 to minus 10 centimeter. To conclude about black hole, should say that almost every mathematical condition that exists for black hole to define their boundary, trap surface to horizon is for the stationary vacuum space-time, or when again they add vacuums, they add it's for how to say this, when they add matter to it, again it can be definable, these surfaces. But there is one condition that around the black hole we have all these activities going on that in turn can affect the black hole physics. And if we want to write a formula for more realistic black hole, we should consider all this magnetic field, all this radiation around the black hole. And we need maybe some new understanding, a new mathematical understanding based on this physical understanding that we have to redefine the boundary of black hole and the characteristic of black hole. And as I said, there is no electric charge in the for the black hole in the nature, whatever it is the interaction with the external magnetic field, which is black hole get discharged by producing this prompt radiation and later by the JEV emission. That's it.
Rahim, sorry for interrupting you. Just I want to let you know you have 20 minutes up to end of your talk.
Okay, so now I will go to the second one. Let me open and reshare. How I can. No, I want to.
So may I use this time to ask a question, short question?
Sure. One moment. First I put other slides, then we will go.
Maybe you have to stop, share, and again share.
Leave the meeting. No. How to stop sharing?
Next to the camera, there is an option.
Okay. Okay. Now I stop sharing. Yes.
Yes.
Can you see my new slides?
Yes. Maybe before going to the next topic, we have a question from
Yes, Soroush, thank you so much. Yeah, I have one maybe quick question.
Yes.
As Reza said, Robert Wang in 1984 or 1974, sorry, he showed indeed that the solution in the presence of vacuum Maxwell equations for a vacuum curve black hole maybe tend to a uniform magnetic field aligned with the rotating axis of the black hole far from the black hole. But interestingly, he showed we have an strong electric charge close to the curved black hole. So how you say you remove this electric charge, but you use the Wald and Papa-Petros solutions? Thank you.
Okay, this electric charge, first of all, it doesn't exist by itself. We have this, let's say, induced electric field. How we can define what is the value of this, let's say, electric charge? We should be able to look at the universe, and GRB will provide us a good example. When we look at this Q/M equivalently, which is by far, GRB is the most luminous the transient event, the Q/M to explain this is less than 10 to -6. So in principle, even in the highest luminosity observed in the universe, we cannot have the charged black hole. But what this charge...
I know. Physically, yes, we have no any charged black hole. Yes, it's true. But I mean, my worriness is about the Wald solution, which contains both the magnetic and electric charge. How you remove the electric charge? I don't know.
How to you mean this
because the solution predicts very strong electric charge close to the black hole. So
no, it doesn't. When we talk about producing very strong, we should compare with observation. As I show, it's not very strong comparing to.
I got your point, but my main question is about the mathematical solutions risen and driven by Wald. But okay, maybe later we can discuss.
May I? Yes. In a moment, the question is the the charge of the world solution is time varying with accretion. And, and the initial charge, by the emission process of vacuum polarization, is discharged, goes to zero. In other words, the world solution has never been duly interpreted physically. The world solution initially has just a charge which is given by the effective charge, which is given by the J, the rotation of Kerr, and the magnetic field B0. This charge, the net charge of the system is zero. Then after the emission of the polarization of the vacuum, that effective charge goes to zero. And the system starts over again with a new effective charge corresponding to a value of practically B0 constant, but with smaller j. Therefore, this we are writing up in the paper that you have heard publicized this morning by Rueda and Kerr. In other words, the effective charge has always been misinterpreted as a real charge, which was then destroyed. No, the effective charge is different, creates the vacuum polarization.
But Prof. Raffini, I understand. Yeah, I understand your comment. But there is another problem, Prof. As you know, sometimes this transition and also decaying to magnetic fields maybe causes to the Wald solution predicts some magnetic monopoles. So if we are worried about observations, but there is no any monopoles, how we can solve these ambiguities?
No, there is no monopole, and the solution of Wald you will see in the paper has no monopole solution, and it's perfectly right. The magnetic field homogeneously outside, and it gets reduced by vacuum polarization, and then the process starts over. The effective charge is the new quantity which we have addressed, the fundamental point, as was introduced by Orge this morning. But don't worry, the paper will soon be ready and we will discuss all the details. By the way, this of the regeneration of the Wald solution has been one of the main missing points in the understanding of the Wald solution. Even the recent article published by some of the British school is missing this key point. The paper should be ready anytime.
Sorry, Professor Ruffini, to interrupting you. I think let's go ahead, and then after that we can continue the discussion. Thank you so much.
Okay, so shall I?
Yes, please.
Okay. The second part of my talk would be about deep learning in astrophysics, which is the result of our PhD student Rastegarnia in collaboration with Wang and Dr. Mir Torabi and Rafai Sadr in Al-Zahra University and Geneva University. The outline of this talk would be, first I will talk about quasars, which in general can be GRB or galaxy or stars, whatever. Then I will be talking about deep learning and convolutional neural network, because Mohammad Hussein talked about machine learning and the whole idea. So I will especially go through the convolutional neural network and explain what is this. Then I will talk about SDSS data. There are many packages to download, but I will represent a way for newbies in this area to go to the website and download and see the data and spectrum by themselves, optical spectrum. Then I will explain a bit about data pre-processing and the importance in astrophysics. Finally, I will be talking about our CNN architecture and the result. So these are quasars which are believed to be powered by a supermassive black hole around million solar masses to billion solar masses. In general, they can study the quasars is important because they exist in the very high redshift, maybe till redshift 9, which, if it is true, it will change the some part of the cosmological history of our current understanding and the understanding of the supermassive black holes. In general, studying of this is very important, but our main goal that we have studied quasar because there are many data of this. So they can, in principle, constrain the cosmological parameter. They can be studied to understand the formation of supermassive black holes, because this is very important in the black hole physics, how these supermassive black holes are created. For the galaxy formation, study the early universe and many other interesting areas of physics, which, when we don't know, first, we cannot classify an object as a quasar. Second, if we cannot measure the redshift, we have missed. If we have missed the redshift, we cannot do anything about this beautiful physics that we can say. The main reason that I said, because we have many samples, for instance, SDSS more than 700,000 quasar data, but supernova around 70,000 and gamma ray bursts around 2,000 sample, or now a bit more. As you can see, when people do, for instance, this Nature Physics, Nature Astronomy paper 2019, it shows that if we do the cosmology with quasars till around redshift 1.4, it's in agreement with previous cosmology obtained from the standard candles of the cosmology. But after 1.4, it shows that we should reconsider our understanding, because these quasars also can exist till redshift 9. So, in principle, these are very important sources to study. As you can see, this is the typical spectrum, flux versus lambda wavelength of the typical quasar. As you can see, it's very rich. It has many emission lines, and this richness can help us to study it better than other sources. So one thing is that imagine 700,000. If you want to see one by one every day, as SDSS has done for data release of 12, I think, they have visually inspected one by one to report the redshift and report that this is quasar or not. After that, after data release 12, which now last year we had data release 16, it's impossible to visually inspect all these sources. So we need to have a human level automated code to reproduce with a high accuracy, the redshift, and the classification for us. Many methods have been proposed, but till now, the one that has been used in the SDSS website is called QuasarNet, which I explained a bit, and I explained the difference of QuasarNet and our net developed for this work that I explained to you. And this is very important because for the first time in SDSS history, among the official reported redshift and reported classification, one reported part is devoted to the machine deep learning, which is a convolutional neural net. So here I will be talking about only supervised machine learning. So whenever I talk about deep learning, machine learning, only supervised. So what is the basic idea? The basic idea is very simple. Imagine you have many parameters. You want to fit it with here like a simple regression with a line and to have a result. What would we do? We say that we have some coefficient to be defined. This is a very simple idea of the behind even most complicated codes in the deep learning. So for instance, here I have many data points. I fit a line, and when I fit a line and calculate this distance, this is the simplest case, which I call cost function. And these distances altogether must be minimum. When I find this minimum, I find this coefficient. And when I find this coefficient, it shows that machine learning has been optimized to find the best solution which can use in the future. So this is this can be considered as machine learning, but is a simple regression. Well, I will explain later what makes self-learning of machine makes out of it. I will explain, but this is the whole idea that you can see. Here I have only one set of data points, but I can have many. And here I have only one layer, omega wx plus b. I can have also many layers, but whatever it is, finally I have a loss function written by this, which by using some optimization method, I can optimize and find this w. So let's go to the convolutional neural network immediately. What's the idea? What's the basic idea? It's simple. If you try to focus on what I say, it's very simple. Convolution means I have an image, let's say 5 by 5 image, and these are the pixels of the image. What convolution does, it's a filter. This we call it filter or kernel. It scans over this pixel, and for instance, when it is here, it divides one by one, like 0 to 9, 2 to 4, 1 by 1. It multiples one by one, as you can see here, and finally it sums all the multiplication and gives a number, which finally this number will be saved here. And as you can see, the 5 by 5 can be reduced to 3 to 3. This is the meaning of convolution. So it convolves this layer by different parts of the image. And by convolve means this multiplications. A very simple idea is that, for instance, I have the edge here. Here is, as you can see, this has been translated into the machine to understand the 6 by 6 matrix. Here is gray, 0 by 0, and 10 by white. This kernel or filter has been written in a way to find these borders. And how it can find, it goes scan through this, it sits here 3 by 3, then multiply 1 by 1, then finally we will have this 0, And if it slides in this one, we'll have 30. Then we'll have, if it slides 2 more, we'll have 30. It slides to all the 0, 0. And what we'll see here, the resolution is not too high, but it shows that there is a border here in between. If we have very high resolution, this border will be shown in a very narrow. So this is one of the ideas of the convolution. It finds the characteristic based on what we have defined for the kernel. This kernel here can find the vertical edges. It can be tilted like 90 degrees to find the vertical, to find the horizontal edges, or whatever else, whatever we are searching. But the beauty, as I said, this is the whole idea of the machine learning. The beauty of convolutional neural network is that it says, okay, instead of this kernel size, I put some unknown values on the W1, W2, W3 instead of this W. Then I start to convolve. At the end, we have this Y, which should be using the optimized optimization of the loss function. We should find what are W1, W2, W3. This automatically machine finds many characteristics that even we cannot understand. Maybe it's the edge or the thing that we cannot see. Machine by optimization of this W1 to W9, or this is 3 to 3 kernel. It can find by itself many hidden, depends how we define for it, many hidden characteristic of the image, or this image can be image of the star, of a galaxy, or it can be equivalent spectrum, which one part is flux and another dimension is lambda, or it can be a 1D, one-dimensional only flux to be fed to the system. So imagine if we want to implement for a classification or implement for redshift recognition estimation, this W1, W2, W3 will be found by machine in a way that all the characteristics, maybe this characteristic is the shifted lines or emission lines, or when there is no emission line, there is another characteristic that we cannot see. So we can rely on machine that if we study more about this W1 to W9, we can infer some new physical understanding of our sources. Here, when I take sigma, this is activation function, which in the machine learning, it can be a sigmoid or tangent or ReLU. It depends on our problem to solve. Usually in many areas, ReLU works well. What is ReLU? Here, 0 to infinity is a linear function, and here is 0. And we'll add to prevent the linearity in the different layer of the of our network. One more thing that we need about, especially when we go to 2D images, is that to prevent losing the information of edges, we add or we pad some extra pixels into our image. We call this padding. And there is another thing, striding, that can help us to increase it can help us to increase the level of deepness of our network, or increase the velocity, the speed of the processing. What is the strided convolution? Is that when I have this blue, if I go with stride 1, I will go the next convolutional, the next filter will be shifted by 1. I call it stride 1. If I shift by 2, I will call it a straight 2. And in how deep we want to
Sorry,
find
Rahim,
the pattern.
sorry, Rahim, for interrupting you. You have 5 minutes.
Okay, I will go faster. So this is striding. It depends on how deep we want to find the pattern. We can stride 1, 2, 3, whatever we want. Another one that we need to take care is the pooling. What is pooling? It defines a kernel and it goes through, for instance, this 4. It finds if it max pooling, it finds the highest, or if it is the average pooling, it finds the average of this 4 and put it in 1. In our calculation, in our redshift, it's better to work with max pooling, which find the prominent lines in our case. But in principle, many of these pooling, striding, or all these things can be adjusted, which we call it hyperparameter optimization by hand to find the best solution. And as you can see, finally, I can have this, I can implement my kernel and add many layers to find as deep as I can go through the data, through this image, and find all the characteristics that I cannot find. The one thing that I didn't mention, when I go through, I can have one of these, like this is the 3 by 3, or I can have, I will explain later, and I call this 3 by 3, I call the kernel size. Here, for instance, if I want to go by PyTorch, this is a very simple coin. There is a neural network sequential. First, I define convolutional neural network 1D for when I have one-dimensional data. This is the inputs. This is the input, the dimension of data. Output, which I explained later after the talk of Wang in the maybe hands-on workshop that we have. We will provide you a code that explains all these things. And this 200 is the size of kernel. Instead of 3 by 3 is 200 here. Then this is very easy. As activation function, we introduce relu. Then we introduce max pooling, and max pooling is stride 2. So in this very simple code, without need to go through the codes to do all these things, by PyTorch we can implement our code. And as you can see, I have, for instance, I have one self-layer 1 I have introduced by sequential 1, the second layer, another sequence, the third layer, another sequential, and all these layers have different numbers that can be changed in order to find the best results. And at the end, we can define the forward propagation, means that what is the order of our layer to be implemented. First layer 1, layer 2, layer 3, and then fully connected layer 1, layer 2, layer 3. And as I said, SDSS has the, in order to be, I want to finish in 5 minutes, maybe when you give me more 5 minutes, I will finish. By far, the most complete quasar survey is SDSS, more than 700,000.
Can you hear me?
Yes.
Yes. It's let's say it's almost finished. How much time do you need to finish?
5 minutes. 5 minutes.
Okay. Okay. Please, if you can speed up, that would be great.
Okay. 5 minutes is enough. For this work, at the end of this talk, we will go and download in the range of 2.8 to 3 the redshift, which has 11,000 spectra, and we will explain how the resolution of data is, and the redshift, we take the redshift as the label to train our network. And the convolutional neural network, as I said, we define the 3 layers with this explanation for one convolutional, one convolutional layer of one-dimensional, then as a ReLU for activation function, then max pooling, and for each one we'll represent different numbers in order to find the characteristic. Here, the one kernel size is 200, it finds the global patterns, and one kernel size is 20, it finds the local pattern. Maybe this 20 is responsible to find the emission lines, and this 200 for their shifting because of the redshift and other values. We don't know exactly. So the redshift in the SDSS, there are many redshift reported, visually inspected is the most reliable one, which we should use this, but today we use a pipeline redshift, which can be downloaded more easily. And as you can see, let me go through this is the quasar net, very similar to our net, but instead of finally finding the redshift, they find the lines, and based on these lines, emission lines, they find the redshift and the classification of the quasar. And as you can see, their kernel size is 100, 100, 100, 100, and maybe that's why some of the result that we can get from our network cannot be found by this network. How to download the data? First, we go to this website, and you would see this. There are many interfaces to do this, but to give you a hint how to do this, the dr16sdss.org, it opens such a page. Then there's optical spectra. When you click on it, there would be such a page, and in the optical spectra, you would go to the spectrum search, and in the spectrum search, you would you can choose redshift 2.8 to 3, and then it shows you all this information. Here, there is a file that gives you the address of all the files to be downloaded. If you are familiar with Python, there is a wget file when you run, automatically it will download all data, all spectrum for you, including the redshift. So, and one of this data that I have clicked on, redshift 2.95, it has many emission lines that you can see. This is the FITS file that need to be downloaded when we do wget of this file name, and then it automatically download all data for us. And finally, one of the most important thing is that to do the data pre-processing. What is why data pre-processing? There are at least 3 important reasons. First is normalization, then it's vectorization, and then handle missing value. Why normalization? Because it will give data in the same range, and it will be easier for machine to deal with it, to find a feature, and to be faster comparing when it's not normal. Vectorization, if we have for instance, if we have the image, we need to convert it to a language that machine can read from pixel to values. And sometimes when we do this, we miss our missed values by the mean value or the median value. And this is the code that we have prepared. It reads all the data that we have downloaded, and then it will reproduce based on this normalization, flux minus average over standard deviation. In principle, you can work with whatever you want, but it must make sense and it must not give you strange values. But this one also is matter of experience. Only 2 more slides.
Sorry, Rahim, if I,
okay.
because we are so much out of time.
Okay, so this is the final slide. This is the architecture of our network. We have the last revision of monthly notice. We will be available on monthly notice soon, and this is our result from other things that we can see. It's for this set of value, it's almost like QuasarNet, the already that they have done, but for whole sample, our net is much better than QuasarNet.
Great.
Okay, that's it. Then we will go through the, after one use time, we'll go through to implement all this thing in a code.
Okay, great. Thank you so much. And maybe you want to announce to the audience that all of this code that you mentioned are available in our Indico webpage.
Yes, exactly. They are available. They can be run. Also, we have reproduced all this data 2.8 to 3, and we have normalized, so people can easily follow line by line to reproduce and change this hyperparameter by themselves. We will talk about this maybe after when you start to have a taste of how this works, how it can be applied for this.
Yes, we have to encourage audience to keep with us and to pay attention to the next talk, because we have a hands-on exercise. So maybe we have time for a very quick question or comment from participant. Is there any question or comment? So if not, let's thank a speaker again, Rahim Moradi from ICRANet, and let's move forward to our next speaker, Wang. Wang, can you hear me?
Okay, thank you. Bye for now.
Thank you so much. Wang, we cannot hear you. So our next speaker is Professor Wang from ICRANet, Italy. He is going to talk about more networks and more areas. And he will continue this data science workshop, and we will have some hands-on exercise with him. Wang, I cannot hear you, unfortunately. Can you please turn on your webcam and also your microphone?
Okay, I'm here. The app just crashed.
Okay, great. Now we have you and we have your slides. So please go ahead.
Yeah, assign me as a presenter. I need to share the screen.
Yes, but I can see your presentation, but let me give you again the access. So please share it again and.
Okay.
So great. Okay, the stage is yours. Please go ahead.
So I will continue Rahim's talk and to extend to more networks and more areas. So first, is from the redshift to classification. I can change Rahim's network a little, then that network can work for the classification problem of the SDSS data. And the second, let's try to deepen Rahim's network to see how the accuracy changes. The first two are working on the real data because SDSS is the real observation, but the third one is on the simulation of a gravitational wave. And also we change the network using the second problem a little. Then that network can also work for to determine if the observation has a signal, gravitational wave signal inside, but we use the simulation data. So I gave a short review. Minimize something. A short review of the machine learning, because I need to give a whole procedure to the participants, then we can change something. So to use astronomy, I think astronomical data records the spatial and the temporal information, which is actually very close to the image recognition and to the speech recognition. So the picture of the galaxies are seen by the telescope, the spectra of the detected radiation, the structure of the universe generated by simulation, all this can be categorized to the image. So we can use the technique of the image recognition on it. And for the time domain data, we can classify it to the voice recognition, so similar technology also. So broadly speaking, there's only axis of our four-dimensional universes. We live in other time and space. So the data is no exception with time and space. So what machine learning has to do is to receive this data and to give an answer. And abstracted to the mathematics, this little robot, where's my mouse? This little robot can be seen as a map, mapping in the data to the answers. And for machine learning, especially for this deep learning, this map consists of many layers of neurons. So this is an example of a neural network. The two leftmost gray dots represent the input data, which are passed into the middle layers, which has 3 layers. And each layer contains 4 neurons. If we know the correct answer, we can define a loss function to compare the difference between the machine's answer and the ground truth. Here I call the ground a loss function. And in the first talk by Muhammad, he called it as the cost function, they are equal. So we have the loss, so we can compute the loss. And for each neuron can be presented by this function as X is the input data, which generally be presented as a vector matrix and multiplied by the weight, the weighted matrix also. The final nonlinear function A acts on the result. So when we train the machine, we are actually fitting this omega. There are thousands of parameters in each omega, and the whole network has hundreds of neurons. So the total number of the parameters reached in the order of 1 million pairs. So to fit such a very large number of parameters, a large amount of data is required. The more data input, the more accurate the fit and the better the prediction ability of the machine. So today in our demonstration, for saving the time, we train just a part of the data samples. We may practice later with the whole sample. So now we have a network and a lot of data. For example, we can train the machine. It is like teaching a child to distinguish a dog from a cat. You show him a picture of cat, he answers dog, you say wrong. You are wrong, it should be a cat. So after many times of training, the child masters the method of distinguishing between cats and dogs. So mathematically speaking, it is to find a set of parameters omega that makes the neural network outputs the same answer as the real answer. So that is the loss function is close to 0. This figure shows the initial omega is at a very higher loss in the red region, you can see. And each time the training, we seek the gradient of the loss to omega. Then we move omega along the gradient by one small step, which is defined, the size of step is defined by eta. So the gradient is opposite direction of the sharpest line, so along this two-dimensional plane. So when you train one step, so you feed the data to the net once, this dot moves a little, you feed the data again, it moves a little, then little by little, finally it reaches the lowest point, the blue, in the blue region. So here you can see in the, I have it on this figure also. So here is how can we propagate the loss from the final loss function and to all the layers. It is done by the partial differentials. So we may go back to here later again. This is what I want to say for the theoretical part. So in first step is to initialize the network. So there are many methods, the Haghighi, the normal, the H uniform, there are many methods. Then we do the forward propagation because we have the initial omega and we have the data. So we compute layer by layer, then to have the loss. So here is the second, compute the loss. So for different problems, we have different definitions of the loss function. After having the loss, we do differentiations and to back propagates to all the omegas and to change all the omegas a little. Then we repeat all this procedure. We change it omega little by little. Finally, we can reach a convergence if you have designed the neural network well and use some optimal methods to training. So here we go to our first example that continues the Rahim's example of predicting the redshift from the SDSS. So we change it to classify the SDSS objects. And from the same data, that is a spectra. Here are just some examples of the spectra. So it's one-dimensional, x-axis is wavelength and the y-axis is the flux. And there are some differences. This slice was shown from Rahim's presentation, and he designed a net like this, and the final output is the redshift. So there's only one value of the output. And we need to change a little bit. We are doing the classification. For the first change is we change the last layer. That is the one value to, for example, we are classifying two classes of the objects. So we change one output to two outputs. And also we need to standardize the output that all the values are between 0 and 1. So we use the softmax function acting on the final output. So this is exponential. And this is a log softmax with a log on the left side. And also the loss function is different. In Rahim's case, he used the mean, actually I don't remember. So but in this sample, I use the cross entropy. The cross entropy is widely used for the classifications. So we need to change two parts, the last layer of the net and the loss function. So after doing this, for example, we predict the two values. So this is the last output. One is the first one corresponds to the galaxy, and the second one corresponds to the COSA probabilities. So if the first value is 0.28, the second is 0.72, then we say it's a COSA. So very simple. Now we can demonstrate the procedure from the notebook, Jupyter notebook. I have prepared two types of notebooks. One is for the core lab, because I need to download a lot of data. I think more than 10 GB of data. So if you are following, you want to run the notebook with me, I think it's impossible because downloading takes too much time. But I have given it here, this core lab. Now I tried to run in the core lab also.
Oh, Wang, could you please share the link in the chat? Then the participant can follow this.
Okay. I shared before.
Okay, great, thanks.
So it's here in the core lab. Imperial core lab does not have all the packages. So first we need to, I uploaded the data to Kaggle. So perhaps Kaggle is blocked in Iran, but Google can connect Kaggle. So you may follow this guide to install the Kaggle package and to download something for downloading the data. So this procedure, follow, run it. And here, this SDSS, this one is the name of the database that I created, that I prepared for all the DR16Q data. And the objects,
Wang, sorry to interrupt you again. Stupid question. Which of these in GitHub we have to choose, because we just open it? Which because there is 1, 2, 3. There is
this one. ICRANet.
Yes.
Second one.
So everyone can choose this second one and then go to the page that you are talking. Okay, yeah. Great. So I wanted to be sure.
So we can take a look at the Kaggle. So here are the data of SDSS and prepared for only having the visual checked redshift data. So here we download two. You see here has many blazars, galaxy, quasars, stars, and since in this example we only classify quasar and the galaxy, so I only downloaded these two files. So download and unzip. Okay. Then I want to run it on my server. It is faster than the collab because the following are the same. So we first input many packages. Mainly the PyTorch packages and the H5py, which reads the H5 format. I'm using the H5 format. So the first step to load the data. And this is here the same. For the collab, it's the same, just a different route. Since I want to run it in this tutorial, so I set the sample numbers to 3,000, about 10% of the whole sample, 3,000, and I have the feature. The feature is just the flux, normalized flux. So I have the normalized flux of the galaxy, normalized flux of the quasar, merge them together. This is merge. Also I merge the label. So the label I set the the galaxy as 0 and the quasar as 1. So as you will remember here, so we have these 2. Yeah, so we export. Finally, we output these 2 values. So if the value final give 0, 1, which means quasar if 1, 0, close to 1, 0, then it's a galaxy. Okay, here just to change it to the format that PyTorch can read. And here is a net. Here we define the net. You remember Rahim defined this net, and I just simply copied that net to here. Only change one line. This is the last layer, a linear layer with input 100 neurons and output 2. See, Rahim has this here's 2, 1, and here I have 2. So let me run it. Run it. Here's some information of this H5 files, 3000. Split the data. Here I split the data to the test sample and the training sample. So I use the training sample to train the net and the test sample to see how well it is. Right. So to define a net, this format is defined by the PyTorch that you need to have a class. You name this class here fnet, simple net fnet, and you write this initial part. This is also this line is common. Then you have the first layer, define what the first layer, define second layer, third layer, and the dropout layer, and these are fully connection layers. So we have here something like here this is CNN. You see the convolution 1D, but we are using the 1D data, so we have convolution 1D. So some convolution 1D and some dropout, not presented in the figure. And the full connected. So here the solid square. And here is the forward function. But here before was just definitions. So in the forward function, you are using these definitions. So self means you are using something inside. So first we have X is input data. So input data to the first layer. So it goes to this layer and doing some computation. And to the second, third layer, then we need to reshape it. When you are writing the code, you will understand these trivial things. And finally, we have the out and returns out, which has 2 values. Okay, we have the class now. Then we generate an object that we call the net simply, and we test it. So we randomly create a value X to see if the net works. Yes, good, it works. The first one is how many sample. The second one is the channel size, because Rahim explained that the CNN, it has channel. So like how many filters, and we generate how many channels. And the third one is the length of the data. The length of data is something like the length of the x-axis, so 4,618. And it gives the 2 value, but this is just random because everything is random. This we will talk later. It's another net. Then we go to define others. So usually we use the GPU, but GPU is much faster than the CPU doing this multi-threads computation. And here to check if the computer has a GPU available. If it has, we use it. Okay, yes, here we have. We have and net, and you see this line. This line we move the net from the CPU, from the memory CPU to the GPU memory. This line. And we define the device is the GPU. And here we define a function to compute the accuracy. So it is computed by comparing 10001 of the prediction. So if it predicts correctly, it gives the 1. If wrong, it's 0. Then we sum up all the 1 divided by the number of samples. We have the average accuracy. And here's the loss function. See, here we go here and follow it. So it's a forward propagation we have shown here. This is forward part. Forward propagation defined. Compute the loss. Loss is here. We define loss is here. So we here define the loss, and it's very easy. The function given by the PyTorch. And the back propagation is this optimizer. So this is we use W to optimize. So this thing defines how this point moves. So it has some, this one is smart. Okay, now here is the definition of the epochs. Epoch means how many times we repeat the training the whole sample data. Batch size means every time how many spectra we input into the network. And here we define a training iterator. So this data loader loads the data. Okay, we go to the main part, training part. So for epoch in range number epoch, so you see, so 10 epoch, so we do the loop of 10 times. We say we start to train the net, and we define the time. This can be useless, and some initial parameters, and train it. This is load the data loader. So we load the data, which has the image label is the classification, the true classification. And if we use GPU, yes, we use GPU. So we move the data, load the data to the GPU, to the device. And first we set the optimizer to 0. You remember, every time we need to compute the gradient, a lot of gradient. So we initialize all the gradient to 0. Okay, this thing we put the data, this image to the net to make the first forward propagation. So we have a prediction. Then we input, so here prediction, and this label just the true value, and computed by this loss function. Now we have the loss. Then we back propagation the loss to all the weights, all omegas. And then we move the omega by the optimizer one step. Okay. Here's just for the outputs. So this 4, you see this 4, okay, this loop. This 4 reads the data, this size of data, the batch size of data, 1, then it repeats till finishing 1 epoch. So till finishing all the sample, and it goes to the next epoch to train the data again. So here, so each epoch we just to show how the accuracy changes, we can run it now. This one should be fast. Oh, I did not run. Crazy. The training is the first epoch, 0.58. Then it goes to 72% accuracy. Then 75, very fast. 78. I defined 10 epochs, so let's run 10 times. So if you have time, you can run much more number of the epochs and use all the data. Here, only 10% of the data. So you will get a much better accuracy. Sometimes it gets worse, but don't worry, it will go up again. And the loss goes down, you see the accuracy goes up. Okay, to finish the 10 epochs. This accuracy is for the training data. So we are training this as a big part of the data. Now we are going to apply our net as we don't know the classification. But we are using the test sample. This test sample never used in training the machine. I think I defined 20% for test. Finished. So this net predicts a galaxy 96.7% accurate, and the cosine is 71. Okay. Now we go next. Next is deepening the redshift net. So if we count the latest neural network structures and refer to the winning networks of some recent machine learning computations, we can see that most of networks use the classical ResNet as a basis. ResNet. This is especially true for the networks targeting one-dimensional data, such as gravitational wave prediction computation, held in Chicago just last month, where the top 3 networks all involved ResNet and did not make complex changes. So in this tutorial, we are going to demonstrate the ResNet, this paper. You may take a look. The citations published 6 years ago, citation 93,000, very popular by Haghighi. So the thought of the network is simple. That the most straightforward idea to get more accurate predictions is to make the network deeper and wider, and to include more parameters and a nonlinear structure. So before we remember, we have the layers, not a lot of layers, yes. So here, if we increase the layers, this is an example of how many 60 or 34 layers. We expect we can make a better prediction, but actually it is not. You see this figure, the comparison between the 18 layers and the 34 layers. The error, okay, this is error, y-axis is the error, x-axis is how many times of the training. Which is the error of more layers. More layers, the red line, is higher than the error of less layers. This problem is a degradation problem. That as the network depth increasing, accuracy gets saturated and then degrades rapidly. But when you have more parameters, it's hard to train, especially, and there are many reasons we can discuss later why it happens. And this paper solves this problem by a very simple, just one line, usually just one line of the code, that do a shortcut connection, which simply performs identity mapping. And their outputs are added to the outputs of the staked layers. So you remember before we have here a lot of layers. Now we have a shortcut. We directly move the result from here and go back to here. So X. So here X. Then add the FX. FX is just here. The past 2 layers. Add it. So So always there is a shortcut to add the original output and give a result. And by applying this technique, you see the right side, the 34 layers, the error, it goes down. Yeah, now it is better than the 18 layers. So why this residue where fx is the residue, works. This is an unanswered question, and many papers are discussing about it. If we have time later, we can talk about it. Also, I want to ask the listeners to pay attention to the efficient net. You see here, this ResNet only go deeper, but efficient net also consider scaling and balancing the depth, width, and the resolution. All makes the net bigger, but I need to carefully optimize the size.
Wang, you have 10 minutes from now.
Okay, good, enough. So we go back to our example. Remember before we used this part, FNet, simple CMM. Now we use the FNet, the ResNet. ResNet consists of many layers. So here define, and each block, like here, each block we call each block. So here we define how each block it is. So we have two convolutional layers of each block, or three, 2 or 3, okay. And then we apply the Bayesian normal. This is for solving the gradient vanishing problem. And then we have the forward. So it's very simple, just like 2 or 3 layers of the CMM here. But the return, you see here the return we have the original x multiplied by the y2 as here, y to the fx here. And this works together to make many layers. So here we define a new net. Now this net we add a module, so we add layer by layer. We added the first block 1, and block 1 I repeated 9 times of this 2 layers residual block. I will define the channels and block 2, 3, 4. So and then I flatten and all the CMM, then make some fully connected layers. Finally, the output is 2. You see here 2. Okay, let's run it again. We restart and run it. What happened? Okay, we can skip the previous net, run the ResNet. Okay, let's take a look at the ResNet. This is its structure. It repeats for. So this it has 8 blocks. Oh, not 8. Sorry, the first type block I gave 9, then 1, 1. So it has how many? 12. So 8, then 1, 1, 1 block, then flatten. Then some linear transformation, fully connected net is other linear transformations. Okay, we test if the net works, how good it works. Again, we are going to train the net. I think let's run, okay, 10 epoch, but this time it will be slower. Because this net includes more parameters, so it will be slower. Okay, while it is running, let's go to the third topic, is to apply a redshift net to a gravitational wave. So here, we know the key is this net. And when we look at the gravitational wave signal, and this is the simulated signal, the blue one. So it's like da 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 da. in the time domain. So this time it's 2 seconds all the time. Usually for the gravitational wave signal, we need to do some pre-processing. So first we transfer it to the, now is the time domain, to the frequency domain. And by applying also a windowed Fourier transformation. And then we cut the band. So here, for example, we take only the from 20 to 500 hertz of the band, then do the inverse transformation to have this green signal. So this is again the one-dimensional data. Yes, one-dimensional. Just the length of the input data is different from the previous SDSS data. So input of these two problems, the one-dimensional, but the size is different. And output, the redshift gives the value on the gravitational wave problem, gives if the input data has a signal there. So again, you see, we only change the very little part of the. Let's see how it is now. It has 3 epochs run. The first epoch, 76, then it goes directly to 97. This net change slower, but it is more accurate, very powerful. And since why it is so powerful? Because we are using only one-dimensional data. It contains very few information. If you are dealing with like 2-dimensional, 3-dimensional data, you may need a larger net or more advanced structure. But more advanced structure are also based on this, usually this ResNet. So here, let's go to see the work on the gravitational wave. This file is somehow a complete, quite a complete example of using PyTorch and for the deep learning. Quite a standard example. And the previous one is very simple. I only wrote the simplest essential functions. So here I.
Thank you. You have only three minutes.
Okay. But they are doing the same work. Like the pre-processing a band pass, what. And here is a model. They are the same model. Just you need to change some numbers here because the length of data is different. But I'm not going to run this one. It takes too much time. This one, it has a lot of sample, but we can take a look at the result. The result is the accuracy reaches like 86% for this very simple one. And the best net in this computation bill, I'm using the data from computation, is like a 88 or 87 point something. So within 1% of accuracy. This is very simple, but comparing with the best net, only 1% of the accuracy difference. Okay, here we almost done. So I want to show you that this machine learning is very easy. Once you master a net or some nets, you can, for one area, you can change, for example, here from the redshift, we were inferring redshift, and now we are doing the classification problem. And also you can extend to different areas here from SDSS to the gravitational wave. If you know how to download the gamma burst data or the supernova or others, because we are gathering more and more information, more and more data by the more advanced telescopes, so we can extend the same method to many different areas. Okay, here we have done. Here the 96, 71. Let's see how it is now. It's 99 and 94. Good. Okay, I have finished. Soroush?
Thank you so much, Wang. Can you hear me?
Yeah.
So great. Thank you for the nice talk. And actually, your talk give us a sense for working with the data, and you know that was a great, and how we can apply to different topics the same methods to get information. So let's see if there is any question or comments on your talk. And also, we would like to inform the audience that they can find the codes and this essential material in the Indico page. Actually, all the information are there. So if there is no question, let's thank speaker Wang again, and thanks all the speaker of the session. And actually, as I mentioned, this workshop session was aiming to give you some sense for working with the data, not having you expert on data analysis actually. So we can finish this session here, and we hope have you all tomorrow morning. Also, tomorrow we have some interesting talks on cosmology, on dark matter, on the history of the astronomy. And tomorrow morning we will start at 10 a.m. in Iranian time, and at 7:30 in Central European time, or let's say Italian time. So since we have so many Italians here, okay, it's good to mention it. So thank you again, and see you tomorrow.